Hello everyone. Today we are starting a periodic classification. Especially I want to start the topics which are very much important for JEE mains as well as for NEET. So in this respect, I am going with the scratch. So just I'm selecting what periodic classification of the elements. So from the very much important topic that is periodic properties. So many of the times these the questions are repeating from this periodic classification and especially from periodic properties. So we are going to discuss in detail with the concepts and the questions, so which are very much important for JEE mains, that is periodic properties. So before explaining this periodic properties, I want to give you one small concept regarding screening effect. So the first chapter which we are going to deal that is classification of elements. So in this classification of elements, so we are going to discuss first important concept, that is what screening effect. So which is the base and which is the important point to understand to know very depth of this periodic classification or periodic properties. So in this case, what is this screening effect? So the screening effect, generally, this is what the nucleus, as the number of shells are increasing while going down the group, as the number of shells are increasing, we know that the nuclear force of attraction will be very less when it comes to the holding the outermost electrons. That means here we know that electrons are revolving around the nucleus. So in this case, the nucleus will hold this revolving electrons. So in this case, what is going to happen? So the nucleus is holding these revolving electrons. Out of this, we throw nuclear force of attraction. Throw nuclear force of attraction. So due to this nuclear force of attraction, what is going to happen? The electrons which are present in the inner shells, so it is also attracting these inertial electrons as well. But when it is attracting these inertial electrons, the electrons are coming closer towards the nucleus. The electrons are coming close towards the nucleus. During this time, what is going to happen? These electrons are also experiencing electronic repulsion. So between these electrons, there will be repulsion. So now, due to this repulsion, so what is going to happen? The electrons will not come closer. So nucleus will have to apply more energy. Nucleus has to apply more energy to counter this repulsion. To counter this repulsion. So due to this reason, so what is going to happen? The effective nuclear charge which is reaching to the outermost electron is going to decrease. So due to countering this inertial electrons repulsion, so the effective nuclear charge decreases. So most of its nuclear energy is spent on countering this electronic repulsion. So this is what the screening effect. So where the nucleus is unable to hold, or nucleus is not able to hold much strongly as compared to inertial electrons, because nucleus is spending much of its energy in holding this inertial electrons by countering the repulsion. So due to this, the effective nuclear charge is decreasing as the number of shells are increasing. So due to this reason, so we can see there will be screening effect, so that the atomic radius increases. So what is the uh, implication of this screening effect? So atomic radius increases, and as well as it has all the properties due to the screening effect. So the chemical reactivity also increases for certain elements. So this is what screening effect, the constant, especially how will you calculate? Through the screening effect constant. Screening effect constant, that is sigma. Especially, what is the effective nuclear charge means? The nuclear charge actually possessed by this nucleus, that is jet, minus the screening effect constant, is called effective nuclear charge. So this is what, according to Slater's rule, according to Slater's rule, we can calculate how much an element can attribute to the screening effect, that is through screening effect constant will be given by Slater's rule, but which is not much important for our examination, so I'm not discussing now. So our main focus was to understand just what is the screening effect. Next, what we are going to discuss, that is periodic properties. So in these periodic properties, first one we are going to discuss is atomic radius. Atomic radius, very important one, that is atomic radius. So what will happen to this atomic radius? So what is atomic radius and how to calculate it? So in general, when it comes to atomic radius, so we cannot calculate the atomic radius directly. So then how it can be calculated? Because the atom is, we cannot get atom in isolated state. So atom is not available in isolated state. So when atom is not in isolated state, so we cannot calculate its atomic radius. Is it clear? So we can say generally these atoms or these elements, they are existing in which state? Combined state. They exist in combined state. Since they are existing in combined state, that is bonding with another element. So since they are very reactive, all the atoms, to attain stability, so they always be found in combined state. So since they are in combined state, how will you find out their atomic radius? But when they are in combined state, when they are in combined state like this, in different ways of combination, how they are combined depending on it, so we can calculate the distance between the two nucleus. We can calculate the distance between two nucleuses. How will you calculate this distance between two nucleuses? Through electron diffraction or X-ray diffraction, okay, or infrared diffraction, so or magnetic resonance spectroscopy. So out of these different methods, we can calculate the distance between the two atoms. So when we can calculate the distance between two atoms, then the half of this distance between the internuclear distance is called atomic radius. So half of the distance between two nucleuses of two bonded atoms is called as what? Atomic radius. Atomic radius. That means let's take this is A atom, this is A atom, like similar atoms. When they have the distance between the two nucleuses, we can find it out, so that the distance we have calculated, and just half of this distance is called atomic radius. Atomic radius. So this is what the concept of atomic radius. Then the atomic radius depends on which kind of bond or what kind of combined state it is having. So in what kind of bond it is forming. So on which this atomic radius depends. So in this respect, we can discuss what are those covalent radius. That means when the compound is in covalent bond, when the element is in covalent bond, what is its radius? When it is in metal crystal form, during that time, what is its radius? And what is van der Waals radius and what are ionic radius? So all these concepts we will see one by one. So here, when it comes to this atomic radius, so depending on the type of bond it is formed, so we can classify the radius. So first one we can classify as what? Covalent radius. Covalent radius. As we know, when the element is in covalent bond formation, so in this covalent compound, so we can say, let's take both are similar elements, let's A and A, both are similar elements. In this case, we can calculate the distance between the two nucleuses through different methods we have discussed. So, and the half of this distance is called as what? Covalent radius. That is, we can write distance between two atoms, we know that is just divided by 2. So this is what? Covalent radius. Like we can say, we can take molecule of H2, molecule of O2, like N2. So these are what? Different similar kind of atoms. Then you have to focus more on this when you are calculating covalent bond. Like as we have seen these three molecules. So hydrogen, if you see, this is formed with single bond. Then oxygen, when you see, it is formed with double bond. When you see nitrogen, it is forming what? Triple bond. As we know that the more is the covalent bonds. That means more is the overlapping. Means more is the strength of the bond. That is, triple bond is more stronger than double bond. Double bond is more stronger than single bond. So that what is going to happen? Due to strength of the bond, due to more nuclear force of attractions between these two atoms, the length of the bond is going to decrease. What is that? The bond length is going to decrease. Bond length decreases. So when bond length decreases because of this, so we can say, what is that? Radius, atomic radius also decreases. Atomic radius decreases. So it also depends on the strength of the bond. That is, if it is triple bond, the bond length is going to be decreased. If it is double bond, even more. But like single bond, it will have more atomic radius or bond length is more for single bond. And for double bond, it is less. Triple bond, even more, less. So this is what we understood the concept of covalent radius. As we are seeing the covalent radius, see the radius, actually the radius should go to this position. But it is coming to this position because these electrons are shared, so that it is attracted by two nucleuses. So the radius further decreased. So this is what? Covalent radius. In this covalent radius, also we can see another kind of radius. What is that we can see? If two atoms are different, if this covalent bond is formed with two different atoms, like we can say HCl, like HCl, if you can see, this is A atom, this is B atom. Is it clear? For an example, this is hydrogen, this is chlorine. So what is the covalent radius? Here also we can see. So there's the distance between these two nucleuses we can measure, and half of this distance is called covalent radius. This is what? Covalent radius. Are you getting my point? So in this case, what will happen to the distance between the two nucleuses? It also depends on the electronegativity of this A and electronegativity of B. Are you clear? So in this case, what should be the distance between A and B? That is, we can write radius of A atom plus radius of B atom minus 0.09 into XA minus XB, or difference of electronegativities. So when two different atoms are reacting, means here what? Bonded means hydrogen is more electropositive, chlorine is more electronegative. So what is the difference in the electronegativity is also determined, because so more is the electronegativity difference. What is going to happen? The bond is going to be shorter. The bond length becomes shorter. When bond length becomes shorter because of electronegativity difference. So due to this reason, what we can say? So the atomic radius also decreases if more is the electronegativity difference is there. Then here, what is Ra and Rb? Is what? Covalent radius when they are bonded with similar molecule or similar elements. Similarly, for second atom, like we can say, if it is hydrogen, we can say covalent radius of hydrogen in H2 molecule. In H2 molecule, what is its covalent radius? There you have to apply here. And similarly, for what is this Rb? It is also covalent radius of chlorine in Cl2. That means in Cl2, what is its radius? Are you getting my point? So that means individual, when similar molecules radius you have to get, and in this case you have to apply, and also depends on these electronegativity values. So then we can calculate what is that called? Covalent radius when both have different electronegativity values. So this is what the case of what covalent radius we have understood. Next we will see metallic radius. What is that? Metallic, or it is also called as crystal radius. So in this metallic radius, as we know that Like if you take copper wire, how it will be? Like complete coppers are there. And this in this metallic crystal, so in the crystal lattice, what is going to happen? See, these metallic atoms are orderly manner. So they have arranged in orderly manner. So in this case, one atom, one metal atom is attached or bonded adjacent to another metal. And all are similar metals. Is it clear? In this case also, we can calculate the distance between the two nucleuses. Then half of this distance is called as what? Metallic radius. Half of this distance is called, this is A atom, this is also A atom. So distance between A and A by 2 is called metallic radius. So again, this is also called what? Metallic radius or crystal radius. That is distance between the half of the distance between the two nucleuses. This is what called metallic or crystal radius. So now when you compare this metallic radius to this covalent radius, obviously you are going to see how this radius is decreasing. Radius is decreasing. When it comes to the compare between covalent radius and metallic radius, now you can observe that metallic radius is more than covalent radius because you see the size here. What is the size? So that's increasing. So metallic radius is more than covalent radius. Then now we are going to see one more kind of radius, that is van der Waals radius. What is that? Van der Waals radius. So in this van der Waals radius, what you are going to observe is, see, van der Waals force is generally it is an intermolecular force. It's a intermolecular force and it's a very weak force. It's a very weak force. That means that this force is existing between molecules. This is force is only between the molecules and it is what? Very weak force. Like you can say, like one molecule is there. This is one molecule. This is another molecule is there. So they are as possible, they are more close to each other. So in this case, what is going to happen? The distance between these two nucleuses, we can calculate, and that half of the distance is called what? Van der Waals radius. Now you can see how much distance it is. So van der Waals radius is always more than, van der Waals radius is more than metallic radius and then covalent radius. Covalent radius. In this case, it can be calculated in what? In their own solid state when they are in this van der Waals radius, first point. And it is especially for whom? For molecules. It is for molecules or compounds. And also, one more important point we can write, this van der Waals radius also considered as it is the radius of inert gases as well. So we can also calculate this van der Waals radius for inert gases as they are existing as what? Isolated atoms, or also we can consider them as what? Molecule. These isolated atoms can be considered as molecules. That's why we can calculate van der Waals radius for inert gases or noble gases. Is it clear? So this is about the concept which is related to different types of radiuses we discussed, and we have also discussed which radius is more and which radius is less. The next point we are going to discuss, that is ionic radius, very much important. So in this ionic radius, we are going to discuss ionic radius. So generally this ionic radius is a part of ionic bond. Is a part of ionic bond. So before formation of ionic bond, so this bond is formed between ions. So what will be the radius of this ion? We are going to discuss first of all. Let's take, I'm talking about this ionic radius. Let's take sodium we can take. Sodium, its atomic number is 11. So number of electrons are 11 and number of protons are 11. Is it clear? And since being a metal, it has the tendency to lose electron. So that what is going to happen? It will lose one electron. When it loses one electron, it will become, number of electrons become what? 10. Now number of protons become, protons cannot be lost because it is inside nucleus. So number of protons, how many protons are more? One proton is more. That is, we can say it is becoming what? 1 plus. Na plus. Why? Because 1 positive charge. Now you tell me, what about their size between neutral sodium and its ion? So you can observe that 11 protons are holding 10 electrons. Initially, it is having how many? Let's consider you have 5 lemons in your hand, large lemons. So, when one lemon is taken out, what is going to happen? You will hold this with the same force for the 4 lemons. So, that what is going to happen? Automatically, the size of your hand is going to shrink because of one lemon is less and same force is applied on the 4 lemons. So, due to that reason, what is going to happen? The size of your arm is getting what? Shrinking. Similarly, the size of this atom for cations will be shrinking. So in this case, size of neutral atom is more than size of its cation. Size of neutral atom is more than its cation. So similarly, we can write for an anion. If you see, let's take chlorine. Number of electrons are 17 and protons are 17 because its atomic number is 17. So what is going to happen? It has the tendency to gain one electron because non-metals being its tendency is to gain electrons. So it becomes Cl minus Cl. Now you can see in this case electrons are 18. Now protons are 17. Now you observe 17 protons are holding 17 electrons while 17 protons are holding 18 electrons. If I increase one more level, what is going to happen? Your size of your arm will increase. So the size will increase. So due to that reason, we can say size of, as compared to size of neutral atom, the size of anion, because it gained one electron, so one electron or one negative charge is increasing. That's why Cl minus. So size of anion is more than size of its neutral atom. So in this concept, if you compare all the ions between cation, neutral atom, and size of anion, so who has less size? That is always remember size of cations. Size of cations is always smaller than its neutral atom. Its neutral atom. This was N for neutral atom, C for cation. And it is always the neutral atom size is smaller than its anions. Its anions. Please remember this. So size of anion is always larger because of more number of electrons. So the effective nuclear charge, especially when it comes to C, when more is the number of protons, effective nuclear charge is increasing. When effective nuclear charge increases, it will hold the electrons with more force, so the size automatically decreases. So this is about ionic radius. Then we'll come to a few examples, like we can say, uh, like we can say like some isoelectronic spaces. Isoelectronic spaces means like we can say C4 minus. That means where it gained 4 electrons and become 10 electrons. And now we can say N3 minus, then O2 minus, F minus, then we can write Na plus, Mg2 plus. So when you write like this, so for all isoelectronic spaces, as you know, as you see, its proton number is 6, atomic number is 6, 7, 8, 9, 11, 12 for magnesium. So more is the proton number, more will be effective nuclear charge. More is the effective nuclear charge for magnesium is more because it is having 12 protons but holding 10 electrons. While here 6 protons are holding 4 electrons gain means 10 electrons it is holding. So 10 electrons it is holding means, so it has with less 6 number of electrons. So it has effective nuclear charge is very less. When effective nuclear charge is very less, it cannot hold the electrons very much strongly. So what is going to happen? The size automatically appears bigger in this case of this. So in this way, it will decrease. Similarly, for if you see for like between two oxygens, like O2 minus and O minus, so it gained 2 electrons. It gained 2 electrons. Same 8 protons are holding 10 electrons. 8 protons are holding 9 electrons. In this case, more is the number of electrons means more will be its size. So in this case, we can write like this. Hope you are understanding. So similarly, we can say Fe2 plus, Fe2 plus and Fe3 plus. So here it lost 2 electrons, but here it lost 3 electrons. So when it lost 3 electrons, means what we can say here, because here effective nuclear charge will be more. So more is the effective nuclear charge because more number of electrons lost. So now more protons are there to hold less electrons. So it will hold with more force. More force means lesser will be its size. Are you getting my point? So this is what about ionic radius. And one more point I want to tell you, in this ionic radius, what is going to happen is like we can say who is the smallest cation and who is the smallest anion we can see. In this case, if you can see smallest cation, the smallest cation in the periodic table. In the periodic table, that is H plus. What is that? H plus. While smallest anion, very very important point I'm telling, this is what? Smallest anion is, what is that? F minus. Fluoride ion is the smallest cation in the periodic table, not H minus, not H minus. Why? If you see, for this answer, we can write electron to proton ratio. Electron to proton ratio for H minus is 2. Sorry, how can you write H minus means it gained one electron. Already one electron is there, it gained one electron. When it gained one electron, H minus means how many electrons become 2 electrons? By protons means 1. So it will be electron to proton ratio will be 2. That means more means here it will experience what? Repulsion. Here it will experience repulsion. When it is experiencing repulsion means, you should understand, repulsion means the size automatically increases. But when it comes to for F minus, its electron to proton ratio is, like you can say, how many electrons? 10 electrons by 9 protons. So it will be 1.11. Here see, electron to proton ratio is 2, while for fluoride ion, electron to proton ratio is 1.11. So it is what? It is experiencing what? Attraction. So more is the attraction. What is going to happen? So it will be experiencing less atomic size. When you see, when it comes to this, what is the size of this hydride ions? Now you can see, I will write it. So you can see fluorine is the least size, then chlorine, then bromine. Afterwards comes, what is that? Hydride. So that means the hydride ion size is more than even bromine ion. That means according to what? According to the ratio of electron to proton. According to the ratio of electron to proton, what is that? You can say the size of hydride ion is what? More than even bromine. So this is the order you should understand, especially from ionic radius. So this is the concept related to all kinds of radiuses we discussed. Next, very much important topic, that is what is the variation in, or what is the trend in groups and periods. So what will happen to this radiuses in groups and periods is highly important. So in this trends in groups and periods, so we will see trend in periods first, we can say. In periods, how the atomic size varies. As we know, for a period, the number of shells remains same, so that after one element to after another element, what is going to happen? Atomic number is increasing. When atomic number is increasing means its nuclear charge or nuclear force of attraction is increasing, so that it will hold the electrons with much more force of attraction. So when it is holding the electrons with much more force of attraction, automatically the size of atom shrinks. So in periods, in shells, what is going to happen? In periods, the atomic radius will shrink irrespective of having similar number of shells. Why? Because effective nuclear charge increases. So atomic radius I'm writing in general, atomic radius atomic radius decreases. Why? Due to increase in effective nuclear charge. So due to effective nuclear charge, increase in effective nuclear charge, atomic radius is decreasing. Are you getting my point? So now you will see the variation how it is going to happen. So if you find it for like second period elements, so since atomic radius, different radiuses we have studied. If all the elements are in molecular stage, that means they are not individual atoms, if you are calculating only van der Waals radius, only for van der Waals radius. If you want to calculate van der Waals radius, that means all these atomic radiuses we are getting from what? From a molecule or from a compound. So that means they are showing what? Van der Waals radius. In this case, for second period elements, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. In this case, so what is going to happen? Here atomic radius is going to decreases. So this is the order. Don't forget that it is we are writing van der Waals radius. If we are writing covalent radius, if you are writing for covalent radius, here you will see the difference. Very much important point. This is lithium, this is beryllium, this is boron, carbon, nitrogen, oxygen, fluorine. But we know that. So here all are what? Here all are what? The covalent radius we have written. So what about neon? Neon's radius should be even more less actually. But neon is not going to form covalent radius. It is being inert gas element. So as I told you, it will have van der Waals radius because it will act as a molecule. Is it clear? So because of that reason, what is going to happen? Among them, all of them, so neon will have which radius? Van der Waals radius. So when you are writing van der Waals radius, so you should understand, we know that van der Waals radius is always more than all kinds of covalent radius as well as metallic radius. That's why neon will have more atomic radius as compared to all other periodic elements when we are considering only covalent radius. But in general, atomic radius, in general, while writing atomic radius, so lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. So the atomic radius is as usual it is decreasing. But noble gases size will be just more than its halogens. Noble gases atomic radius is just more than its halogen. Beside halogen, that is, if we are talking about neon, so neon has more radius than fluorine. When we are talking about general atomic radius, this is what the case. So all kinds of cases we have done. Similarly, for we can write also for this is for group 2 elements, period 2 elements I have mentioned. Similarly, you can also write for period 3 elements. And in this case also, sometimes if you closely observe what is going to happen, nitrogen's size is similar to oxygen. Generally, we can say. And also, what is going to happen if you write in more advanced concept? So, what is going to happen here is oxygen size is more than fluorine than nitrogen. If you observe, the oxygen size is 0.74 angstroms, while fluorine is 0.72 angstroms, and for nitrogen it will be 0.70 angstroms. So this is what their sizes, atomic radiuses. So if you go more closer, why the size of oxygen is more? Because what is going to happen? If you write electronic configuration 1s2, 2s2, 2p4, in this 2p4, when electron is entered into this 2p4, so these 4 electrons, they will experience electronic repulsion. So due to this electronic repulsion, obviously the size of, size of oxygen atom is getting greater. But you can say, even fluorine has more number of electrons as compared to what? 2p5. For fluorine is what? 2p5. So here also should experience more electronic repulsion. But here what is going to happen? So this repulsion is dominated by, what is that? Effective nuclear charge. Effective nuclear charge is dominating electronic repulsion. So due to that reason, the size of fluorine is little bit shrink as compared to oxygen. So this is what the concept, which is more deeper concept. Is it clear? And due to this reason, this is what the general characteristics. And we have to see for, if you see the similar trend, we are going to see for third period elements. Now we can see for, what is that called? Transition elements. For transition elements, like d block elements. So in these transition elements, so what will happen to their atomic radiuses? So if you observe for scandium, vanadium, titanium, so in this case, as we know that electron what is going to happen? Atomic size will decrease while going in a period. So same thing will be applicable here for scandium, vanadium, titanium. Till titanium, atomic radius is decreasing. Atomic radius is decreasing. But when it's starting from chromium onwards, from starting from chromium 2 till if you see copper, the size, atomic radius is remaining similar. The atomic radius is remaining similar. But when it comes to zinc, it is getting more. So actually atomic radius should be what? It should keep on decreasing. But when it comes to from copper to zinc, what is going to happen? The atomic radius is getting increased. Is it clear? And since we are talking about d block elements or transition elements, here noble gases will not come. So in this case, atomic radius is decreasing. In this case, from chromium to copper, atomic radius is getting similar. For zinc, it is increasing more than copper. Why this increase and why their atomic radius is getting similar? So this is very much important point you should understand. It is due to two reasons. Very much important reason is so these electrons from chromium to what is that copper? For all of them, what is going to happen? These are d block elements. So the electron is entering into d subshell. But from chromium onwards, what is going to happen? The pairing of electrons starting. What is that? Pairing of electrons starting. So due to this reason, what is going to happen? First of all, poor screening effect. Poor screening effect of 3D orbitals, okay, or 3D electrons, we can say 3D electrons, and as well as what is that? I told you the mention electronic repulsion. As pairing starts, what is going to happen? Electronic repulsion. Electronic repulsion happens. So due to these two reasons, what is going to happen? Size is getting abnormal. That is, they're showing similar size, and when it comes to zinc, so electronic repulsion is maximum. Electronic repulsion is maximum because of pairing. Because of pairing, what is going to happen? Electronic repulsion maximum. So when repulsion happens, the size of atom is getting increased. So this is how this atomic radius varies, or how it is showing some exceptions. See, as we are discussing, so we are not just talking about general trend, how it will vary. So we are also seeing the exceptions. So when you read more exceptions, then it will be more chances so that we can uh, do well in the examinations. Is it clear? This is for trend in period. Now we will see what is the trend in groups. So as we know, so trend in groups. So in this trend in groups, as we know, while going down the group, what is happening here? Number of shells are increasing. So number of shells are increasing. As number of shells are increasing, as you are observing here, so the atomic radius is increasing. Are you getting my point? So these are vertical columns, groups are means vertical columns. So in this case, what is going to happen? While going down the group, number of shells are increasing. The large electron is entering into every time entering into new shell. So due to that reason, atomic radius is increasing. When atomic radius is increasing, so as you know, more is the number of shells. Here you will see screening effect. What is happening? Screening effect. So in this screening effect, we know screening effect will be shown more by S block, S of shell, then P, then D, then F. So when D and F electrons are what? They will show poor screening effect. What is that? Poor screening effect. So why they will show poor screening effect? Because of their larger size. See, we know that S and P block elements, they have smaller sizes. First of all, spherical and dumbbell, and they are also very much close to nucleus. But when it's come to D and F block orbitals, F orbitals, what is going to happen? They are having larger size, so that when electron is entering, so it has ample of space. Ample of space is available. So due to ample of space, what is going to happen? So the electronic repulsion is not much possible when it comes to D and F block elements. That's why they cannot screen. So that means nucleus is not going to utilize its much energy to counter that repulsion, because there is no much repulsion. So nucleus will not give its energy to counter the repulsion so that it has maximum energy to hold outermost electrons. So this is what happens: lanthanide contraction and actinide contraction, or transition contraction. So transition contraction is because of d orbitals poor screening effect, and lanthanide contraction and actinide contraction because of what? Poor F electrons, poor screening of F electrons. Due to that reason, what is going to happen? As we understood, so the size of the atom is going to shrink because there is no much energy is utilized by the nucleus to counter the repulsion. So much energy is available with the nucleus. Now with that much energy, it will hold the electrons very much strongly. So size will shrink. So now when it comes to this general category, so in groups, what is going to happen? Atomic radius increases. Atomic radius increases. Like we can say for group 1 elements. So for group 1 elements, we can see for higher, especially from lithium, sodium, potassium, rubidium, cesium. And we don't talk about francium because francium being a radioactive element. Is it clear? So atomic radius is getting increased for group 1. Similarly for group 2, beryllium, magnesium, calcium, strontium, and barium. Similarly for halogens, we can take group 17 elements of fluorine, chlorine, bromine, and iodine, and astatine. So in this case, what is happening? So the atomic radius is increasing while going down the group. This is what generally which is happening for these group elements. But when it comes to some d block elements, so there shows some exceptions. There shows some exceptions. What are those exceptions? When you see zirconium, when you see zirconium and hafnium, So after zirconium, what is coming? Hafnium is coming. So we should expect that as well going down the group, number of shells increases. When number of shells are increasing, the size of hafnium should be more than zirconium. But in actual practice, what is happening? In actual practice, zirconium size is getting similar to what is that? Hafnium. Okay. Similarly, one more example. Why I will tell you. So in the case of what we can say niobium and tantalum, Here is also we should expect that tantalum's size should be more than niobium, but niobium size is more or less similar to tantalum. And one more case, what we can say that is yeah, this one. And similarly, we can say for indium and thallium. So between indium and thallium also, what is going to happen? There also sizes getting similar, atomic radiuses are getting similar. Why these similar radiuses? In spite of having more number of shell than previous element, because this hafnium, this tantalum, this thallium, they will, and also one more is there tungsten. It will also all will experience what? All are experiencing what? Lanthanoid contraction. So what is this contraction? As I told you, so these elements, the electron is entering after filling 4f electrons, or after filling 4f subshell. After filling 4f subshell, the electron is entering into these elements. So that means this 4f subshell or this 4f orbital has, what is that I said? It is having poor screening effect. So that nucleus is not using much force on this what? Repulsion, because of they have larger size. So for repulsion there will be less energy is expended. So due to that reason, what is going to happen? So more nuclear force of attraction is what? Available for holding outermost electrons with much more force. So due to that reason, what is going to happen? The size of atom shrinking. So due to that reason, hafnium for tantalum and for thallium, what is going to happen? They are getting what? Because of this lanthanide contraction, their sizes are getting similar in spite of having more number of shells. So due to what we can write? Due to poor screening effect of 4f electrons. So this is what we have understood. And similarly, we can say like aluminium. After that, we can say gallium. So with aluminium and gallium, what is going to happen here? So gallium is coming after aluminium, so that we can expect that gallium size should be more than aluminium. But what is going to happen? In reality, the size is similar because of poor screening effect of 3D electrons. What is that? 3D electrons. So due to that reason, what is going to happen? Gallium is showing what? Similar size with aluminium. So it is also called as what? Transition contraction. We can say transition contraction. So these are what we have understood how this atomic radius and what are the different types of atomic radiuses and how they are varying in groups and periods. Is it clear? In the next class, we will be dealing with more topics like ionization energy and electron affinity and electronegativity and more oxidation properties, metallic radiuses, okay, and their acidic and basic properties. So everything we are going to discuss. And thank you. Have a nice day.